My name is Mark Denavit. I'm an associate professor at the University of Tennessee, Knoxville. I've sort of a lifelong interest in structural engineering, which didn't vary as I went through undergraduate and graduate school, and certainly in practice, and then as in the position I have now. I got started working with IDEA StatiCa about 5 years ago. The company was looking for university partners in the US to help verify and advance their software, and that was something that I had a keen interest in, and was happy to be one of the partners. So I teach several structural engineering classes, including an introductory structural steel design class for undergraduates at the University of Tennessee. We go a little bit into connections in that class, but I recently started a new class at the University of Tennessee for advanced undergraduates and graduate students, specifically on structural steel connections. And that's rewarding to me because it's a personal interest of mine, but also because of the reaction from the students. This was actually one of my biggest enrollment classes for one of my higher level classes at the University of Tennessee. The students really seemed to respond and be interested in the idea. So, at the college level, one of the biggest challenges for students is understanding the nature of connections. So their behavior, their the physical orientation of all the members and components, as well as the limit states. All of this is like three-dimensional, and so much of the learning material that's out there is 2D. I would say in practice, engineers have a better feel for the physical aspects of the connections that they're working with, but often they'll lack some of the technical background and rigor that usually comes from the classroom. So the gap I was aiming to address with these learning modules is that connection design is often taught in a really procedural way. Students may learn how to apply code equations, but they don't really necessarily have a clear understanding of how the connections actually behave. The inspiration for these specific learning modules to fill that gap was my experience performing verification studies for IDEA StatiCa. I would run one analysis, change a parameter, then run it again. The whole time I'd be doing that, I'd be observing the effect on the deformed shape, the plastic strain, bolt forces. And I walked away from these verification studies, not just with the results I was looking for, but really a clearer understanding of connection behavior. The virtual laboratory approach means treating a software, in this case, IDEA StatiCa, as an experimental environment. So this is somewhere that the students can explore structural behavior in a more hands-on way. In these modules, the students build models, apply loads, and directly observe the results of the analyses, such as the deformations and the development of yielding. So in this way, the software behaves like a laboratory experiment, except the specimens are digital and can be modified instantly. What makes this effective is that it turns abstract concepts that can be discussed and written on a whiteboard into something that the students can see and interact with. They can change a detail, something like bolt spacing or plate thickness, and immediately observe how the load path shifts or how the failure mode changes. And that immediate feedback, the time there, just the fact that it's so quick, helps them connect cause and effect in a way that's very difficult to achieve through traditional lectures alone. This is also something that encourages active learning. Students aren't just receiving the information, they're testing ideas, making predictions, interpreting results. I mean, that's the goal of these learning modules. This process of that active learning and that active participation in the module helps develop a much more deep and durable understanding of the structural behavior, which really hopefully leads to some better engineering judgment.